First of all, thank you so much for the organizers for putting such an amazing event together, and thank you guys for coming to listen to my talk. So my name is Natasha, and as you mentioned, I'm a research engineer at Google DeepMind. Before that, I've been in this role for about 8 months now, and before that, I was doing my PhD at the University of Chicago in medical physics and computer vision. So let's go. I'll skip this. First of all, I would like to start with the overview of current challenges of the radiology field. Radiology has been growing in a very, very fast way pretty recently, and this is partly due to medical imaging technology becoming much faster and more sophisticated. But with this sophistication comes much longer image evaluation and image interpretation. Sorry, I didn't really expect that they were gonna go in bullet points like this. Anyways, furthermore, the amount of data available to analyze is also growing exponentially, and this leads to the gap between the radiologist supply and demand. It's growing pretty fast. And at DeepMind, we are trying to kind of solve these problems using machine learning.
Your necklace is hitting the mic.
Oh, thank you. That's good. All right, but before building any machine learning model, I think it's very important to understand whether this model is going to bring real impact clinically, especially in the medical field. And to answer this question, we build very close collaborations with the clinicians in the field. And these multidisciplinary collaborations of research scientists, research engineers, and clinicians help us answer the following questions. First of all, we really they help us understand the clinical problem and patient pathway. Second of all, it helps us understand the clinical use case and then further define the machine learning problem. Then also, we understand how to define the clinical metrics and the success criteria, of course. Okay. So at DeepMind, we have a few projects in the healthcare space, but I will have time to go over only 2 of them. One, breast cancer screening, and another one is referral from the OCT retina scans. So let's start with mammography, and this is the project that I've been working on since joining DeepMind, so it's very close to my heart. So first of all, I would like to motivate our work in this space. I'm showing you this world map, which shows the country and each country and the top cancer per country in 2018 among women. And pink here is showing breast cancer. The bright orange is showing you here the cervical cancer. And you can clearly see that breast cancer is dominating here. And this is true. Breast cancer is the most commonly diagnosed cancer among women worldwide. And in 2018, about 600,000 women died from it. And in 2019, about 300,000 new cases are expected to be diagnosed. So it's a huge problem in the world. For those who do not know, mammography is the most commonly used clinical imaging technique for breast cancer screening and diagnosis. Mammography is just an image of a breast. It's just a 2D projection taken with an X-ray. And this slide shows you an example of left and right breast of screening mammograms for 63-year-old patient. And on the right corner, I'm circling a suspicious region with calcifications for this patient. And you can clearly see this is a very busy image. And for our human eye, it's very difficult to see these abnormalities. Of course, radiologists are much better at doing their job, right? They probably can spot this, but still, for them, they're still prone to human error. And mammography does suffer from false positive mistakes as well as false negatives, and we want to reduce that. So at DeepMind, we are collaborating with Imperial College of London, NHS system, as well as Cancer Research UK to build an algorithm that will reach the human performance in breast cancer diagnosis based on screening mammograms. Unfortunately, I cannot share any more details with you because it's an ongoing project, but please stay tuned and hopefully you'll hear from us soon. Something actually I wanted to mention, I forgot, is that going back to the close collaborations with clinicians, I'm working almost every day. I talk to our radiologist from the field, and his insights into just image interpretability as well as disease extent has been driving my work constantly, has been driving the development of the algorithms constantly. All right, so next project is ophthalmology, and here DeepMind is collaborating closely with the Moorfields Eye Hospital, and it's one of the largest hospitals in London, and they have a special unit for eye problem diagnosing. Due to the aging population, it's expected that we will see a huge increase in blindness in the next few decades. However, it's also expected it's also thought that about 80% of the vision problems can be cured if you diagnose it early enough. So this is an incredible space for us to make an impact on sight loss. In August of this year, so a few months ago, my colleagues published a paper in Nature Medicine on the diagnosis and referral in retinal disease. Unfortunately, I was not a part of this project. It's amazing, and I'm very lucky to be presenting the results and the work on behalf of my team. So first of all, when a patient gets to a hospital, they get this 3D image of their eye. And you can see an example on this slide. The image is optical coherence tomography or CT scan. After so actually at DeepMind, what we wanted to do, we wanted to use these images and create and make an algorithm that will have a referral suggestion. So based on the image, does this patient need is the referral urgent, where a patient needs to be seen within days and treated within days? Then semi-urgent, when the patient needs to be seen within weeks, routine, and observation only. So these are kind of classification outcomes. Let me just put it all up. So we developed this framework that is two-stage, basically. In the first stage, we have an ensemble of segmentation networks which take an input of the OCT scan, and they produce an output of the tissue maps. So you can see it in the middle. And these networks were trained on about 900 OCT scans here that were sparsely and manually segmented. The second part of this whole architecture is the classification network. And the classification network takes an input of the tissue maps and outputs a probability of the diagnosis or referral, decides on what referral this patient needs to get. Compared to other architectures, this architecture or this pipeline has two key components and advantages, I would say. First of all, the segmentation network provides you interpretable results. It tells you what it sees at every position of the image pretty much, which is very useful for a clinician. And second of all, the the second part of the architecture is completely scanning device independent. So the network learns the fundamental knowledge about the human eye anatomy and pathology, and it doesn't really care if you presented an image from a different scanner. And finally, we achieve expert performance on this task, on the referral task. To evaluate our algorithm, we took an eye scan, OCT scan, from the first visit of the patient. And to get the ground truth labels, we took additional images. We inferred the ground truth labels from the additional images and follow-up patient history. And we evaluated our algorithm using ROC analysis. This slide shows you the ROC curve for the task of urgent referral classification, because ROC analysis is typically used for binary classification. So here we are using either urgent referral or everything else. And our algorithm achieved the AUC, or area under the ROC curve, of 99.2%. And for those who do not know, the closer to 100, the better. And actually, whenever you see this curve, you want it to be the closer to 0-100 corner. And we are pretty close to that. We also compared this algorithm to the human performance to 8 expert radiologists, expert doctors, eye doctors. And these dots show you the performance of these 8 experts. You can see that only 2 of them come close to making urgent referral as accurately as our algorithm. But of course, it's unfair comparison, because typically doctors, they look at previous eye scans. They also look at patient history data. So we did comparison where we gave the doctors additional data and compared to our algorithm performance, but I'm not going to go into details of that, and I will ask you to read the paper because it's brilliant. Yeah. So here, this slide, I also, just to go back to the point that the second stage of the architecture is completely device independent. This slide shows you images from 2 scanners. So you can see clearly the top row and the bottom row have completely different structure and just overall image characteristics. So when we present our segmentation network in an image from a new device, it outputs some garbage segmentation, right? And of course, because the second stage classification network is operating on the segmentation, it outputs very bad final prediction on the referral. So to overcome this, what we did, we retrained the segmentation network on the images from the new device, and the segmentations became much better. So the segmentation network learned the new type of the device image representations, and the classification became much better as well. But the key point here is that we did not need to retrain the second part, the classification part of the network, and that means that we do not need additional data and additional historical data from the patients to retrain it, which is a huge benefit because the medical data is pretty scarce. So I think this is pretty much it on the work at DeepMind. Thank you so much.
Any questions from the audience?
Yeah, hi. Thank you for your talk. It was really interesting to hear about it. I have a question regarding the breast cancer. I have just seen a study that said, analyzed data about mammography. How do you say that?
Mammography.
Mammography.
Yeah, or
And
mammogram.
despite mammography getting better and better, the mortality rate of breast cancer patients does not decrease. And the author suggested that we are kind of overdiagnosing it, or like that abnormal tissue not necessarily leads to cancer, and this exposes women actually to a lot of unnecessary procedures. And yeah, I would be interested what you say to that.
Absolutely, I completely agree with it, and I think it's one of the biggest problems, the false positives that we create, that radiologists create. I didn't mention this, I was going to, or maybe I did, about 50% of patients get false positive calls, which is not a good idea. And I think the algorithms, based on the literature, based on what I've seen, they help reduce these mistakes. Yeah.
Thank you. Oh, sorry. Very nice talk. So 2 questions, I suppose. With the false positive and false negatives in radiologists, do you find that it's sort of consistent across the board, as in this, all radiologists tend to make the same mistakes, or it's very individualistic? And then also on the second part, I saw that you had a distribution of probabilities for the different classes. Do you find that there's any images that tend to be confused, as in they tend to have a fairly even distribution across several classes? And do you think there could be any emergent things there, like some sort of coagulation as perhaps understudied currently and could be suggestive to clinicians?
Okay, so for the first question, radiologists do make, so in UK, first of all, US screening programs, they're very different. In UK, there is a double read, so there is a first radiologist, then a second radiologist that does the reading, and usually you want them to be detecting very different things. So that kind of answers your question. And when looking at how the radiologists perform, they're pretty different in their experience and how they perform in terms of false positives and false negatives. And I guess we want the algorithm as well to be somewhat orthogonal to the radiologist's performance, maybe. And the second, could you repeat the second question? Sorry about that.
Yeah, no. So I was wondering, there was a distribution of probabilities for the classes, and I was wondering if there was any images that, so the example you had was very confident, it was like 99% in one class, but was there any that were, say, evenly distributed across several classes, and could that suggest that there's something starting to emerge that's perhaps understudied currently or underdiagnosed that could be used by clinicians?
Yeah, that's a great question. And you were talking about the RC curve probably. Yeah, so this is, the RC curve shows you performance on the entire data set. So it's across all of the images that we have for OCT scans. But going back to seeing something early in the images, it's definitely the case. And sometimes when the algorithm flags an abnormality, when the radiologist or the eye doctor goes and sees this image and they're like, yeah, I should have probably seen it earlier. So it's another potential area of research where maybe we can try to detect something early in the scans.
Hi, thanks for your talk. So my question is related to the first question that was asked regarding the false positives, and the paper mentioned that I haven't read, I don't know, that the mortality rate hasn't decreased. It could be the false positive to an extent, but it also could be that the treatment is not suitable, good enough, that even if it is a true positive, but maybe the treatment, because I think there were some papers which I haven't followed closely that many, if not most, of the breast cancer patients don't need chemotherapy or the treatments that were used so far. So maybe it's related to that as well.
I'm out of time. Can I answer it, or should I take it offline?
Give a short answer.
Okay. So with I don't know about this paper. I haven't read it, but I should look at it. But what I've seen before, from my understanding, the mortality rates are actually decreasing. And because, first of all, breast cancer is being caught much earlier. And if you catch it earlier, you can cure it much earlier too. But in terms of treatment, treatment also is becoming much better from what I know. But I agree there's a huge room for improvement because it's not, breast cancer has there are so many types of it and so many grades and the way it's developing. And I think there's a lot of research being done on how do we treat these specific categories of it.
Thanks, because there is, to my knowledge, a big shift now in terms of treatment that it needs to be much more individualized.
Yeah.
And not one size fits all. Or,
Yeah, exactly.
Thanks.